Okay, so everything up until this point in Unit 1 is focusing on if the acceleration is constant. Now we're going to look at what happens when the acceleration varies with respect to time. So recall that instantaneous acceleration can be determined by taking the derivative of velocity. So A is equal to dv dt. Okay, so that's what we've done so far. Now we can use integral calculus to go the other way. In fact, if you look at our graphs here, if I go down the graphs, that means I'm taking derivatives. So it's a nice transition from x is parabola to v equals is a line to a equals constant. If I want to go the other way, I need to take integrals. Okay, so integrals are the other side of calculus. So for us to do that, okay, we can find the velocity by taking the integral of acceleration. So velocity is the integral from t equals 0 to t of a dt. Basically, if we do a little bit of algebra at this point in time, right, we're going to multiply both sides by dt, and we get a dt equals dv. Well, to get rid of the d, we take an integral, okay, which is it's called, another word is an antiderivative, to get to this equation right here. Much like we can find the displacement of an object by taking the integral of the velocity equation. So if I take, we know velocity is dx dt, tells me that x, or delta x, is simply going to be the integral from t equals 0 to t of v dt. Okay, now we could do, this one's a little bit easier to clean up with its algebra. In fact, this is also like delta v, so it would be something, it would look like v equals v0 plus the integral of a dt from t equals 0 to t, much like this would be x equals x0 plus the integral of v dt from t equals 0 to t. Okay, and so let's look at an example using this this concept with integrals. So an experimental vehicle starts from rest at t equals 0 and accelerates for a few seconds at a rate given by a is equal to 7.0 meters cubed per second times t. What is its velocity? And then what is its displacement 2 seconds later? Okay, so for us, so this is our acceleration. So what we need to find is the velocity, right, of this acceleration function. And so that's really where this difference is going to come in now. If they're looking for, if the acceleration is not constant, they're going to give you an equation with respect to time. So it's going to be v equals the integral from t equals 0 to t of 7.0 meters cubed per second t dt. Well, what we can do is we can take this out. I'm going to drop the unit just for simplicity. Okay, so now we have this function of 7.0 t equals 0, right, from the integral of t equals 0 to t of t dt. Well, integrals, if I have t to the n, right, I'm taking the integral, it's going to be t to the n plus 1 over n plus 1. Okay, that is our general power rule for expressions like this. So it's 7.0. Well, this is t to the first, so it's going to be t to the n plus 1 over n plus 1. And we're going to evaluate that from 0 to t. Well, this is 0 to t piece just simply tells me that my function, my velocity, will be 7.0 t squared over 2, right? Now, we don't have an initial velocity because it tells us that it starts from rest. And so this is my velocity function. Okay, and so now I'm going to do v of 2, and so that's going to be 3.50 t squared, so 3.50 times 2 squared, or 3.50 times 4. So 3.50 times 4 is 14 meters per second. Okay, so now let's find, so that's part A. Now let's find part B, which is the displacement. So delta x is going to equal the integral of v dt from t equals 0 to t. And so we have our v function, which is this 3.50 t squared. Okay, and so now my delta x is just going to be, so it's going to be 3.50. I forgot my dt here. So it's going to be t to the n plus 1, so 2 plus 1 is 3, over n plus 1, so it's 3.5, or 3.5 over 3. And we're going to evaluate that from 0 to t, which just means my function is going to be 3.50 thirds over t cubed. And so now I can plug in my delta x of 2, because we're looking for after 2 seconds. So 3.50 divided by 3 over 2, or times 2 cubed. And so it's going to be 3.50 times 8 divided by 3. And we're going to find that its displacement was 9.33 meters. Okay, so again, remember when the acceleration varies, now we got to bring in this, we got to use integrals versus we have to use derivatives.